Okay, welcome everyone. Who's done multi-threaded programming? Right, and keep your hands up if you've struggled with it at some stage. It's pretty difficult. These are some of the quotes I've collected on the internet. And the kind of problems you get, we're fairly familiar with all of the things that can go wrong when you do concurrency, particularly when you've got shared writable states. So if you've got some variables that more than one thread can access, this is the really hard thing, one of the hardest things that we do in programming. Also, we're told. I'm going to tell you that everything you've heard is wrong and that programming concurrency is easy-ish. Just like programming your business and application logic is easy-ish. What is difficult is allowing the two to mingle. If you keep your concurrency concerns and you allow them to infect your business and application logic, that is what really makes it difficult. If you take all of the state in your business and application and you allow that to become subject to concurrency concerns, that is very difficult. But if you can isolate, keep the concurrency isolated, it actually is manageably easy. So essentially, the problem is one of separation. And here's an example. Now, this is a link query which computes the prime numbers in the first million integers. Now, how this query works isn't particularly important, but what matters, it takes a while to run. So we could benefit by parallelizing that, so by dividing up all of the work and splitting it up between all of the cores on the processor, and then running it and then collating the results together. So this is parallel programming. Parallel programming is one very specific kind of concurrency problem, and it's not the only one. But this is a very interesting one, because if we want to parallelize, if we want to use all of the cores, how do we do this with that query? Did someone say plink? Yeah. Cool, that's parallel on it. Now, how easy was that? That's just adding a few characters of code. There is no concurrency, messiness, or concerns in there at all. Now, inside plink, as parallel is part of the .NET framework, it was introduced in .NET Framework 4, and it parallelizes that query. It takes a compute-bound, a compute-intensive query, and distributes it amongst all of the cores on your computer, executes them, and then collects the results back together. Now, underneath the covers, there's a lot of work in that. That is a difficult thing for them to have written, plink. But all of that complexity is entirely isolated from the query. So we can do parallel programming with link queries without any complexity. Now, this is an example of where that separation is working really well. And in a way, it's a bit of a simple example because we've written it functionally, non-side affecting, pure, but also this is a structured concurrency scenario. Now, what do we mean by structured? And that is that the concurrency starts and finishes in the same place in our code. It's very tidy, and that makes it easy to isolate the concurrency. Now, but most of the apps that we write and we have to deal with, the concurrency concerns are unstructured. Things start and finish. It's scattered across different parts of the code and scattered across at different times. So here's an example. Let's say you want to write a web browser. So user navigates to a URL. You start downloading that. So you're doing all this network activity. And as those bytes are coming down, you're displaying it on the screen and rendering it. Then you come across an image. So now you have to initiate, sometime later, another parallel download of that image. And then you download some more HTML, another image, you initiate yet another parallel download. Now the first image is finished, so you want to now update the screen to show that first image and redo your layout, and so on. And so there's a lot of concurrency that's going on, and that concurrency is scattered across your program, and it's also scattered across time. It's intrinsic, the data we're working with is not spread out across space, it's spread out across time. We don't know what this HTML and images are until we actually get to that point. So, and another interesting thing about the web page scenario is, unlike with the parallel programming, the work is mostly I/O bound. And I/O bound concurrency means that we are waiting for something to happen. Right? The contrast to that is compute-bound work, where we're getting the cores hot. We're doing something that's compute-intensive. So anything that's not in compute-intensive, that takes a while to run, is I/O-bound. We're waiting for something to happen. Now, a web browser is both I/O-bound and compute-bound, right? There's a bit of compute-bound stuff in there, especially if you've got Flash enabled, and especially if some ads pop up. Now, so unstructured concurrency, this is the difficult thing. Data spread out over time. It may be compute-bound or I/O-bound. Question is, can we separate our business application logic from the concurrency logic in these unstructured scenarios? If we can do that, we can make life a whole lot easier for ourselves, just like we did with P-Link, with that S-parallel. And it turns out we can, but it requires language support. It requires features that we've only completely got in C#5. Now, functional programming diehards have had these things for a while in niche functional programming languages, but a mainstream language has only recently had these features. Now, C#5 is a mainstream language because not only can you use it to target the desktop, which is not going away, and the server, but you can also use it with Mono and Xamarin. You can use C#5 and all of its goodness and all of its features to write applications for iOS and Android, and even Windows Phone and WinRT. So it's pretty much got all of the bases covered when it comes to developing applications. And this language has the power that you need in order to do this. But it also requires a mind shift because we're very used to programming the old way. We're used to doing, I guess, what you could describe as space programmers. Now, you imagine that you've got a desk and everything you need is laid out in front of you on that desk. You're doing your tax return, and imagine that it's all on paper. So we've got everything on there on our desk, and we're algorithm-centric. So to do a tax return, you follow a series of steps, and be 10, 12 steps. Some of them involve looping and repeating over things. So we do all of these steps, we follow them, and then we keep needing data, bank statements and so on. So what happens is that whenever we need data, we reach for it across space, our desk, and if it's not there, we go away and get it. We go to the filing cabinet, our email, and we just block until we get that. So we follow an algorithm. It's very much a space-centric world. So we've become space lords, and that's the way we think. We need to make a shift and become time lords. We need to treat time as a first-class dimension. So here's space programming. We think in terms of execution, and typically it lends itself to pull-based programming because whenever we need something, we pull that data in. What's the opposite of pull programming? It's push programming, right? So when you're doing push programming, it's event-based. So when the alarm clock went off this morning, it was pushing a bit of data onto me that I need to get up and not sleep in. And then that gets pushed onto a bit of code, my algorithm, which is to hit the snooze button. So that's the opposite as push. But we typically tend to program in pull-based when we're doing space-based programming. So whenever we need some data, we pull it in, we grab it from the internet or whatever. And if it takes a while to execute, we just block while it's executing. So we ignore the latency when we're doing pull programming. Now, what is wrong with ignoring the latency? The user gets bored, right? Is one problem. But even if the user says, well, I'm going to end this application or cancel this operation, the whole thing frosts over, right? So, but what happens really when you've got a long-running operation and you just block, that method now becomes a long-running method. Right? Now, what's wrong with a long-running method is that it forces the only way, there's two options. You've got a long-running method and you're in a rich client. You either call that method and your UI goes unresponsive, or the workaround is that the caller of that method runs your method on another thread. Right? This is the concurrency scenario. So any long-running method, if you want to be responsive, you spin up another thread, whether it be with task.run or new thread or threadpool.queueUserWorkItem. However you do it, you spin up a new thread, and you run that method on a new thread. And then what happens when you run that method on another thread is that method, any shared state that it accesses, now is infected with concurrency concerns. And that means all of your application and business state that method accesses is now subject to concurrency concerns and all of these threading problems. So you've allowed these things, these concerns, to mix. This is one of the root cause of the problem that creates the complexity. Long-running methods force the caller to initiate a thread-based concurrency to obtain a responsive application, and then your shared writable state leaks out into your application. So this leads to the first law of time. There are 4 laws of time to becoming a C# time lord and treating time as a first-class concept. And the first one is no toxic long-running methods. It's toxic if it accesses shared writable state, business and application state, and it's long-running if it takes more than 50 milliseconds. That's where we draw the line in the sand, and that means no blocking. So what do we do instead? We do asynchronous programming, right? Now, what does asynchronous programming mean? It's a way of dealing with latency without blocking, and an asynchronous method, it returns quickly or immediately to the caller, and it initiates the operation, it simply initiates it, and then sometime later, when it's finished, it calls you back, right? And that callback that happens once at the end of the operation is called a continuation. Now, what's interesting about asynchronous programming, that is the mechanics, that is the plumbing, but there is something that really makes an asynchronous method significant and interesting, and that is that the asynchronous method takes responsibility for its latency. That is what really distinguishes it. So that makes it an adult in a temporal or time-based world. So that means that if it's a compute-bound operation, then it will start the thread, and because it's starting the thread, it can know how to ensure that any business state is not accessed on that thread. So it can prevent that leakage of the shared writable state because it's initiating the concurrency. It's not the caller that's initiating it, it's initiating the concurrency. It also means that because it's initiating it, if it's doing something I/O bound, it might decide that it doesn't actually need to type a thread at all for the duration of that. So it can also do it more efficiently, and it can make it more scalable. And that is really what defines an asynchronous method. It's one that takes responsibility for its latency. It's an adult in the temporal world. So how do adults behave? Well, they take responsibility for latency. So if they can't do something straight away, they don't keep you waiting, right? They'll say, I'll get onto it, I'll get back to you, and it's done. They also can deal with failure, and they can cooperate and work together with other adults to create greater structures. Let's have a look at that one, failure, first. Generally, if you're dealing with children or romantic partners and something goes wrong, they will respond in one of 2 ways. Now, silent sulking basically means ignoring the exception. So we just ignore it. Maybe we log it somewhere, but it doesn't get propagated. And a tantrum means we take down the entire process when something goes wrong, which is, again, not what we want. So these are 2 things. This is something we need to deal with asynchrony. And the other thing is composition. And what this means is that if we've got lots of asynchronous operations, we want to be able to coalesce them, to have them work together, to create another asynchronous operation. We do this with space programming, with values. We've got all of these patterns for making values and sequences work together, so why shouldn't we have patterns for making temporal things work together? And this is essential to make this effective. Now, here's an example of a very simple asynchronous method. Now, let's work. That highlighted delegate is a continuation. This method, it fetches a web page, we tell it the URI, and then we tell it a delegate to execute once it's finished. So this is an asynchronous method, and this is how we would call it. Get web page async, give it a URI, and then say, when you're finished, continue by writing the result of the HTML out right to the console. Now, this takes responsibility for its latency. It returns straight away to the caller, and it will fire that continuation sometime later. But is it an asynchronous adult? What about failure? How does it deal with failure? it's got two options, right? It can ignore it, it can sulk, or it can throw a tantrum and take down the whole app. There's no way it can communicate a failure to the method that calls it. Right? So this is one of the, when you're coming up with patterns for asynchrony, this is one of the first things you think of, but this doesn't work because it doesn't allow for fault propagation. It also is not composable. If we've got lots of methods like that, we can't make them work together. So what is the correct way to write an asynchronous method? So what are they, in Framework 4, they introduced a class that is called task. Right now, a task, this is how we would write the same thing with task. So rather than returning a void, this returns a task of string, which this means it says that sometime in the future, I'm going to return an object which sometime in the future is going to make a string available or an exception available. So there's a name for this construct. A task is, the computer science term for this is a future. It says, I promise to get back to you in the future with the result or the exception. And it has a whole lot of methods and properties on there, but only two of them matter. The continue with method lets you attach a continuation. It lets you say to that task, when you're finished, fire off this bit of code. That's the first one that matters. The other one is the result, because when that bit of code runs, that continuation runs, it's going to need to know what the result was. So that result property, when you access that property, it will give you the result. What happens if you try and access the result property if the task faulted? It throws an exception. It rethrows. That's the mechanism for propagating the exception. So this allows us, this is an asynchronous adult, so now we can propagate failure, and we can also compose these things together, which we'll look at in a moment. Now, before we go and demo this, there's an important concept, which is that the issue of time and concurrency. The two are related. When you are doing concurrency, you are doing time. And sometimes it feels like it. But it doesn't necessarily have to be the other way around. Concurrency intrinsically involves time, but time doesn't have to involve concurrency. You can program time without programming concurrency, and that is much easier. Anything that you can reduce to a time problem rather than a concurrency problem is going to make life much easier for you. And we do this all the time without realizing it. We just need to do it more. So we can do time without concurrency. In fact, here's an example. I've got on one side, on the left, we've got the space, which is the typical application of business logic in there. And on the right, we've got all our concurrency logic. That's the hard stuff in red. What we want to do is shrink that down and then replace most of it with time logic. Time, easy, concurrency, hard. So this is one of the strategies we've got. So let's have a look at how we might do that right now. So what I'm going to do, we're going to do all the demos in LinkPad today. Now, if you've not used LinkPad, it's a code scratch pad, and it's got an extension method called dump, which lets you write anything out in a kind of a rich way. But one of the things you can do is you can dump any rich client control, Windows Forms or WPF. You can simply dump them, and it will actually render it, and it will spin up a message loop. And the threading model you get is exactly the same as what you get in a real application. The only difference is you don't have to bother with all the ceremony of creating a Visual Studio project. You don't have to create XAML files and prick yourself on all the sharp angle brackets. So, okay, so I've created an example here where I've created a label. This is a WPF label, and I've simply dumped it out. So there it is. So we could take this and surround it in a for loop, and we'll put 5 of those in there. And now we've got 5 labels. These are 5 WPF labels, and we can attach events to them and play with them. This is a great way of doing it. So what I'm going to start with is this example here, where we've created a label, we're dumping it, and we're creating a new timer, dispatcher timer. This is a WPF timer. Now, the way that timers work in WPF and Windows Forms and Silverlight and Windows RT and iOS and Android and Mac OS is that any event that fires on a UI timer always comes in on the UI thread. So you have one thread which does all of your UI stuff, and everything goes back to that one thread, and any timer events fire on that one thread. That makes life simple for developing rich client apps. So I've created one here, and on the tick event, what I've said is update the content to the datetime.now.toString. So this fires every 100 milliseconds by default. Let's run that. And so we've now got the label updating every 100 milliseconds with the time. And we could, if we want, wrap that in a for loop. And we're going to put 5 of them in there. So now we've got 5 timers all going at once. This almost looks like we've got concurrency happening, right? But what part of that code is concurrent? None of it. It all runs on the UI thread. We have 0 concurrency concerns. And if you've ever programmed before handling events in the UI using UI timers, you'd probably be surprised at how relatively easy it is. You don't have to worry about multi-threading concerns. This isn't too hard to do. So the trick is we've kept everything on the one thread by using this timer. So that seems pretty simple, right? We're doing time programming. We are not doing concurrent programming. And this is easy, and this is great. So how is it that we go wrong? Right? How do things go wrong? Let's change this example a bit. What we're going to do now is I'm going to set that timer up just like I did before, but now I'm also going to create a button, dump it out, and when you click that button, I'm going to call this method called runCalculation. And that's going to create a new label, dump it out, and say the answer's 42. Let's run that. Click it, and it says the answer's 42. Now, that was pretty straightforward because this executed instantly. It wasn't doing any work. What happens if we give it some work to do? So let's run this one again. What we're saying now is content equals the sum of square roots. This method here now is doing a link query which works out the sum of the first 10 million square roots. So that's going to take a while to run. Let's see what happens now. We run this, we click it, and it freezes. It locks over. The whole user interface stops while that's running. This is what we want to avoid. So to make this responsive, the kind of traditional approach is we just run this on another thread, right? So task.run. That's going to solve our problem, right? Will that work? No. No? Well, let's see what happens. In fact, nothing's going to happen at all because it's... And the problem is we're actually trying to we've created a new thread, and now we've created a new UI controller label. We've added it to the existing control, and there's no way, you're not allowed to do that in WPF or any rich client framework. You've got to use, if you wanted to make any changes to the user interface, you have to do all of that on the same thread whenever you're interacting with UI controls. So this isn't going to work, but even if it did work, even if we worked around that problem, even if we marshaled back to the UI thread to create that label, there's something else we're doing that's very insidious, in that what we're doing is that everything, all of this code here, is now running on another thread and is subject to concurrency concerns. So that includes this property here. Now, this is thread safe, right? It's just returning a constant. But most likely in real life, that would not be returning a constant. That would be going away to somewhere else in the program to fetch that number. Let's say it's calling a method on an interface. Now, if you're calling a method on an interface, how do you know what code's actually going to run? You don't. That's the whole idea of an interface, right? So that could be calling any code. It might be going to a configuration file, loading up an XML file and feeding into a configuration, fetching it from a database. All of this stuff, it could be accessing all of this code in our program. All of it's happening on another thread. Is that code thread safe? Most likely not. So we have allowed concurrency concerns to leak out by doing this. This is what the pernicious problem we have with concurrency. So what we need to do instead, undo that, we need to make this an asynchronous adult. Right? So rather than returning a double, I'm going to have this return a task of double. And now we're going to return task. So we take responsibility for the concurrency here, which is what we're doing. We're going to start up a task. So we're just going to run this compute-bound code on another thread. But because we are taking responsibility for concurrency, we can clearly see in here that this is shared state we're accessing on another thread. So what we'll do instead is change that to a small n, and we're going to capture that one there on the calling thread. Right, so now we've now isolated that contagion to purely the bit of code that actually needs to run on another thread. So our concurrency code is now only one line of code. So that looks pretty good, right? Should we run that? I think we should run it, just to see what will happen. What's going to happen when we run it? What's the answer going to be? The answer is a task of double. Can you see what the problem is? What we've done is we've said the content equals this. Now, this returns not a double, but a double in the future, an object called a task. So when you call to string on that, which is what WPF does, you just get task of double. So we need to unwrap that value, right? We need to get the result. We want the result of the task, not the task. So how could we solve that? We could put result in here, right? Is that going to solve it? Well, let's have a look and run that. We run it, and we're back to square one, because this result property, it blocks, right, so back to square one. So what we need to do instead, what we really want to do is to jump forward in time to when that task is complete. But we can't do that, right? We can't jump forward in time. Time travel is not possible. Well, maybe it is. Let's listen to a clip from the master himself.
People assume that time is a strict progression of cause to effect, but actually, from a non-linear, non-subjective viewpoint, it's more like a big ball of wibbly-wobbly, timey-wimey stuff.
Okay, so how do we do wibbly-wobbly in C#? What's the wibbly-wobbly operator? What's the operator that jumps forward in time? Await. Exactly, we've got now an operator that will literally do time travel. So all we have to do here is add this magic keyword, await, in there, and it will make us also write this async in here, make that work. And now this solves the problem. This does time travel. So when we click this, we hop into the TARDIS. Sometime later, we hop out of the TARDIS, and there's the result. Now, what we're doing with this, the way the TARDIS works is it picks up the synchronization context. So because we're running rich client, when we hop out of the TARDIS, we will always hop out on the same thread we came in on, right? So that way it maintains that this entire code becomes single-threaded. The other thing it does is fault propagation. So if that operation faulted, when you come out of the TARDIS, it will re-throw the exception onto you. Right, so you get your fault propagation. And what that means is you can handle it with a normal try-catch block. If you fail to put a try-catch block in there, it propagates up the call stack, just like with the synchronous method. So simply by doing nothing, you fall into the pit of success when it comes to error handling. So with await, it jumps forward in time, and it allows us to program the future as though it were present. And it's also allowing us to maintain our pull-based programming model here, because what we're doing effectively is we're following an algorithm and we're pulling the data in as we need it. But we can pull without blocking. Normally pulling means blocking if there's latency. But with await, we can pull without blocking. Now, how would we do this if we didn't have await? We could do a callback, right? So we could do something like this, right? So this is what we'd have to do. And this is very, very roughly what the compiler translates an await into. And what we're effectively doing by doing this is that and this is a simple example. I mean, if we were inside a loop, or had a more complex call graph, the translation becomes really messy. And this is why asynchronous programming doesn't really work without await. It just gets too complicated. But the reason it's complicated is what this is doing is when you use this continue with method, is you're converting your pull-based code sort of into push-based code. Because what this is saying is that when the result of this becomes available, push the result onto this piece of code here. Now, which is better, pull code or push code?
So they're the same, but one's easy to read.
One's easy to read. It actually depends on the scenario. Sometimes push code is the most natural way to do something, and other times pull code is the most natural. In this case, pull code is most natural. So we want to be able to program in the easiest, most natural way. And this is very important for simplicity. And the await lets us do this. It lets us do pull code without any of the costs. OK, so this leads to the second law of time, which is to isolate concurrency from not just from space, but from time, and to favor time over concurrency. So what we did, if we'll slip that back again. Let's go back to the previous example. What we did with this one here is this code here, right, is concurrent. Would you agree? This is running on another thread. This is the example with the wait. But what about all of this code here? Is this concurrent code? Looks concurrent. We've got async, await, task of double. Are we doing concurrent programming with that highlighted code? No, we're doing time programming, right? We're doing the easy time programming. So what we've done is our old solution where we used task.run over the whole thing, all of this became concurrent, right? Now what we've done is we've ended up with only this piece of code here being concurrent, and all of this code here is now time-based code. It's purely concerned with time, which is much easier. And you might think, you're probably scarred, you're battle-scarred from all of the multi-threading and asynchrony you've done in the past, and you do not want to do asynchrony unless you absolutely have to. But the thing is, by embracing asynchronous functions like this, you're voluntarily taking on easy time code to avoid difficult concurrent code. So this is something you shouldn't be scared of, is using this wherever you can, because by putting this into the easy time bucket, you're saving that insidious creep into the hard concurrency bucket. So there's our second law of time. And the third law of time is to use the TARDIS. The TARDIS, it jumps forward in time and allows you to program the future as though it were present. OK, we're going to look now at the composition. We talked previously about an asynchronous adult takes responsibility for its latency, and it can deal with faults. But what about composition? And to give an example, here we've got a query which uses an asynchronous method in the framework which downloads a string from a website. So this returns a string in the future. That's what task string means. And this means jump forward into when that's been downloaded. So we'll run that. This will give us the length of that web page, which is great. That's 13K. Let's do that twice. I'm going to download 2 web pages. And what this says, OK, we're going to jump forward in time to when this one's downloaded. Then we're going to start another download off and jump forward in time to when that one's downloaded. So we're doing this sequentially. So when you introduce a wait like this in different parts of your program, you're maintaining a sequential flow. You get sequenced by default whenever you await a future. But what if we actually want to run this in parallel? So we might want to download those 2 web pages together. That would be quite useful. So to do that, all you really have to do is to start the asynchronous operations without awaiting them immediately. You just await them later, right? And to make this easier, there's something called a task combinator. This static method task.whenAll, what this does, it returns a future that completes when all of the futures you pass to it complete. So it combines many tasks into one task. And this is a really useful construct, because when you're doing this, you're simplifying your code because you're not adding any extra concurrency logic. You've isolated that concurrency logic to that task combinator. And this task combinator, the way they've written it, this is now doing them in parallel. This is a nice fast internet connection we've got here on the Ethernet. But the way they've written this is an implicit part of a task combinator is the fault handling policy. So the fault handling policy, this is really important in concurrency fault handling, and every combinator will have a fault handling policy. And when all, the fault handling policy is that if any error occurs, it will assume that the functions you're calling are impure, they're potentially side affecting. And so it takes the least performant approach. And I think this is wrong because I'm usually, when I call task when all, I call it with pure functions that are non-side affecting. So I wanted one with a more performant fault handling policy. So I decided, well, why not write one? So here's one. This one is called purely when all. I've written a task combinator which takes a params of tasks, just like the real when all, but it's got a more performant fault handling policy in that if any of them fail, as soon as the first one fails, it immediately fails the combined task. And then it ignores the others. Now, writing something like this, it's a little bit tricky, right? If you look at this code here, we've got 2 awaits in a row. It's a little bit tricky, and we are doing concurrent programming. But this is a good thing because we're isolating the concurrency to a testable method that's got no application and business logic to it. We've avoided mixing this with our business logic. By writing a task combinator, you are creating a separation between your business logic and your concurrency logic. So how do you test something like that? How do you know that method works? Unit tests? The problem with unit tests is you cannot reliably unit test concurrent code. It can work fine in the unit tests, but then what happens in production when the timing is different is it fails. There is only one way you can validate a method like that, and that's peer review. You can post that on Stack Overflow and say, hey, my colleagues reckon there's a race condition in there. What's the story? And you'll get 10 replies and a consensus on whether it works or not, what you have to do to make it thread safe, or even if what you're trying to do is completely silly and you should rethink it. And this is a big advantage of this approach, because if you had all your business logic in there, you could not post that on Stack Overflow. Right? The only way this can be peer reviewable is if you isolate it. So you're purely solving the concurrency problem at hand. The only shared writable state that you're allowed is that is directly connected to the concurrency problem you're trying to solve. So the fourth law of time is to compose. Apply composition patterns to time and concurrency objects. We'll look at a bit more of that in the future. And when you think about it, we do this all the time with space programming. When we're programming sequences, when we're programming our application, we're constantly coming up with new patterns, design patterns, to compose things together. Things like dependency injection and strategy patterns, factory method, all these techniques we're applying to space. It's simply a question of doing the same things with time constructs as well and concurrency constructs. So here to summarize, these are the 4 laws of time. No toxic, which is shared application state, long-running methods, separate space from both time and concurrency, use the TARDIS to program the future as though it were present, and use composition patterns on both space and time objects. So this kind of summarizes the issue with latency. So latency is the idea there is a value. We don't know what it is now. We know what it is. It's going to have a value in the future. We want to abstract away that pesky detail that we don't know what the value is, that it is in the future. We want to program it as though it were present. That's latency. But there are other kinds of time-based problems too. And another one is, what about a value that changes? So we've got a value that changes over time, over and over across time. Another way of looking at the same problem is streaming. So we've got a whole set of values that are arriving in drips and drabs. And that's really just another way of almost saying the same thing. So we've got the idea of values that we're getting over repeatedly. Rather than just getting one value in the future, we're getting a whole stream of values across different... That's the streaming problem. So now, with streaming problems, they tend to naturally lend themselves to push-based solutions. right? So push-based programming tends to be more what you would naturally do with these kind of things. And we've already got a construct in C# for dealing with this. We've had it since C# 1. What's that construct called? Think values that change. How do we deal with a value that how do we monitor a value that changes? Even simpler. What's the C# construct for events? Exactly. So we've got events for doing that. Now events actually work quite well in that they are purely time-based. They don't act to introduce concurrency, right? So they're nice time-based constructs. But what do Time Lords think of events? Are they good? Do they obey the 4 laws of time? They obey the first law of time, but what about the other laws of time? Well, let's have a look and see let's have a look and see. Well, and this is an example we're going to use. We're going to imagine that we're running a ER department, and we need to monitor a patient's heartbeat. So every time the heart beats, an event fires. We're going to handle that event, and we're going to use it to run our hospital. So here's an example. We'll start with a simple event. I've created a label, dumped it out, and now I've just handled the mouse move event. So this is just a summary of how events work. And so as we move the mouse over here, it updates the content with a position. This is our little intro, and now we're going to do a heartbeat with events. So what I've done here, I've created a method which will fire a heartbeat event every between 700 and 1200 milliseconds to simulate a heartbeat. So what it does, we've got a while true loop. And this creates a random number between 700 and 1200 milliseconds. And what this code here does, it says, jump forward in time that amount of milliseconds. Right? Rather than doing a blocking sleep, we're going to do time travel instead, because we're all over blocking now. We're always going to do time travel. And then we're going to fire the event. And our payload on the event is simply a number. So we're going to have 1, 2, 3, 4, 5, 6, 7, and so on. So let's run this now, and we should get, we haven't hooked it up yet, so we need to go to the next one. Here we are. Now I've attached event handler in there. So we've got an event handler, called start on it, and let's run that. So that's pretty straightforward, right? That works. It's okay. But now we don't really just want the event. We need to know the beats per minute. Right, so let's work out the beats per minute. To do that, we need to add this extra logic in our event handler. Right, we need to do this arithmetic to subtract the time. Run that, and we'll get a similar result. But it's kind of a bit erratic. What we really want to do is average it over the last 3 heartbeats. Right, how do we do that? Well, we can write more code. We can do anything with code. So I'm creating a rolling buffer with a queue. And now this gives me the average of the last 3 heartbeats. This is something you might do with an event. So now we're getting a rolling average. Now the problem with what we've done here is that all the logic we've got for working out this rolling average and for working out the beats per minute, it's not reusable. We've sort of hard-coded it. We've intermingled it with our event handler. And this is a problem with events. When it comes to composition, that 4th law of time, events suck pretty badly. You can't even get a handle to an event. You can't, say, take one event that takes another event as an argument. Right? You can't pass events around. You can't do things with them. Events are not programmable. So how else could we solve this so that it was programmable? I mean, one idea is rather than having an event, we could have an IEnumerable. So here's an example. I've created now a method called getHeartbeats, returns an IEnumerable int, creating a new random number, while true. And now I'm sleeping for this amount of time. I'm blocking. Well, we'll ignore that for now. We're violating the 1st law of time, but we'll ignore that for now. But we're then doing a yield return. And so what this is going to do is that we can do a for each over this, and we're going to get the same thing we had before, right? But the number of beats. But now, when it comes to working out the beats per minute, and doing that rolling average, look what we can do. This is really cool. We can write an extension method called time interval, and even how that works is unimportant. We can collapse that. Right? We can simply now call .time interval as an extension method on get heartbeats. And I've got another example here where I've done the same thing and I've worked out a rolling buffer, a buffer method. And again, how that works is not important. But all we need to know is this is now what we can now write this as a query. So we've created two reusable methods, time interval and buffer, and we're using a link query to work out the beats per minute. This is so much tidier and composable. This satisfies the fourth law of time, of composition. But of course, we've now broken the first law of time, all right, because we're blocking. So what we really want to do is we want to combine the best of both worlds. We want the programmability of IEnumerable, but we really want a more asynchronous approach that avoids blocking. Now, there's two ways we can avoid blocking there. One of them, and before I say that, I should also point out why specifically blocking is so bad. Let's say we were monitoring not one patient, but we were monitoring a ward full of 100 patients. The only way you can make that work is with 100 threads. It doesn't scale. And similarly, if we wanted, even if we had those 100 threads, if we wanted to then, say, do a query across multiple patients, each one's running on a different thread. So now we're going to get nasty threading problems, concurrency problems again. So this is not a scalable solution. We have to get rid of that sleep to make it work. We have to asynchronize that to make that work. Now, there's two ways we can asynchronize it. One is we could, instead of doing the thread sleep, we could just do an await, a task.delay. Problem then is that what will it return? If this returns IEnumerable event, if we were to put an await in here, what would it return then? Yeah, and well, actually, it wouldn't even do that because the problem is this is an iterator. So it wouldn't even compile. But we wouldn't want it to return a task of IEnumerable event because when you think about it, that would mean it's returning an IEnumerable event in the future. Right? It's returning the whole thing sometime later. We want it to return one, then the next, and the next, and the next. So the IEnumerable interface just cannot do that. It cannot do what we want. We want an async enumerable interface, right, where we change the move next method into a move next async that returns a task of bool. Right? Now, this is getting complicated and messy, right? And the compiler wouldn't support it. So are we overcomplicating things? Is there something else we could do here? And what we're trying to do is we're maintaining a pool-based approach here. And while pool-based programming is really good in some cases, I said before that these streaming change scenarios tend to lend themselves well to a push-based approach. Anyway, and that's why we didn't have the problem with events. Events are push-based. So could we make a push-based version of IEnumerable? Would that simplify things? What would it look like if we had a push-based version of IEnumerable? And does such an interface already exist in the .NET framework? Did someone say IObservable? Let's have a look. Here it is. So on the left-hand side, we have the pool-based, the IEnumerable and IEnumerator. Those are the pair of interfaces. And on the right-hand side, we've converted those. Right? We've dualed them into a IObservable, a push-based. Now, the guy that did this was Eric Meyer. He did this at Microsoft. He did most of the work on Link, on the compiler team. And essentially what you do to convert the two is dualing is a process when you've got one thing which depends on something else, A and B, and you've got an arrow that points from A to B. You reverse the direction of the arrow. It's dualing. When you're doing pushing and pulling, you're reversing the direction of the data flow. And in this instance, we're reversing it now. So what happens now is the observable, it literally is like an event. You can think of it as an event. It follows the observer design pattern, the gang of four design pattern, just like events follow the observer design pattern, but this does it in a programmable way. Events are not programmable. This is programmable. So with this interface, we've got the on next, on completed, and on error. And these things, they fire, on next fires whenever there's a new item. On completed fires when the thing's finished. And on error is when there's an exception. Now, whereabouts is the on error on the left-hand side? That does look a bit odd, doesn't it? I've got an on error on the right and no on error on the left. Where's the on error on the left? Exceptions, exactly. There's a hidden contract there, which is that whenever you call move next, that can throw an exception, right? So that's now made explicit when we do all that. So let's have a look and have a play with that now. Have some fun with it. So what we've done now is, now the other thing that I'll mention is that the interface all by itself is not much work. It's not much use. What we need is a way to have all of the standard link query operators plus a whole lot of extra ones already defined for us. And similarly, when you think about enumerable, how often do you implement IEnumerator and IEnumerable? Almost never, right? You use iterators, but even how often do you use iterators? Rarely. You use link, right? We've got so many high-level constructs we use. Similarly, with observables, we don't usually implement them. We use a library called reactive extensions, which was Eric Meyer's work, Microsoft, and that's available on NuGet, and it's also open source, and it's also available now for Mono and Xamarin. So if you go to NuGet, add NuGet package, and there it is, reactive extensions, and you download that, you can now program, you get all of the link query operators, all the standard link query operators are there, plus ones like time interval and buffer. These ones are exactly like the one I wrote for enumerable, except they work for observables. So there's two parts to it. When something returns an observable, and how this works is not important. So when something returns, it's like it's returning an event. Two things you can do with it. You can attach a query to it which wraps it, giving it more functionality, or you can subscribe to it. Right? So subscribe, this is exactly like doing a plus equals on an event. So when you see subscribe, think plus equals. So we're going, this event plus equals console.writeLine. So we run this now. We're going to get the same thing we had before. But now this is non-blocking. Right? This is a non-blocking push-based approach. So we've got all the programmability of enumerable with a completely asynchronous push-based approach. Now, I said before that in LinkPad you can dump anything. So rather than subscribing to it, we can simply dump. Well, I can do that. Now it will actually, LinkPad will display a sequence which will actually grow in time. So an observable is like an asynchronous sequence. So it actually renders it as it's growing. And that call to normally dump is a blocking method. If you call dump in LinkPad, it's like calling console.writeLine. It blocks, splits, finishes. But this is an exception to the rule. When you dump an observable, it makes sense to subscribe to it. Subscribe is like doing a plus equals on an event, non-blocking. So subscriptions are non-blocking in general. The other nice thing about reactive extensions is that it introduces concurrency only when you ask for it or when it has to. By default, it's a time-based. It's purely time-based, but it's not naive about concurrency. We'll do it if necessary, but by default, it keeps as much as it can in the easy time world and as little in the hard concurrency world. So we've got I've got an example now. I'll factor this into a method, and I'm going to dump two of them at once. So we should see two of them simultaneously now coming. 2 heartbeats, we can monitor simultaneously. And we can also, there are query operators that combine multiple observables together. So combine latest takes the latest value. Whenever one of them changes, it creates a new pair. So we're now, I've got the 2 patients, we're monitoring them, and now it's giving you the heartbeat of each one whenever one changes. And there are numerous, all the joins are there, and there are numerous methods for working with multiple sequences. This stuff really is used heavily in finance, in stocks and trading. But you can use it anywhere that you would otherwise use events. it also supports time travel. So you can await an observable. So what this does is it takes the first 10 items to an array, but rather than waiting for that, it jumps forward in time to when those 10 items are available. So when we run that now, the query is finished, successful, done. But sometime later, when those 10 are available, it's just going to spit them out. It's going to jump forward in time and spit them out. Hopefully, there it is. So that's how you can await it. Now, let's have a look at let's play with RX. And one of the things they've done is, so that you can avoid using these nasty events and just use observables, they've created methods to convert events to observables. And I've written a couple of extension methods to help with that. So I've got one here. This is a WPF project or a script. I've created an extension method called getMouseMoves, which converts the nasty mouse move event into the nice observable of mouse event args. And I'm using this helper method here to do that. So I've also created a helper method to set the position of a canvas on WPF. And what this does, it creates a whole lot of labels, adds them to a canvas. And then what it does is, for each of these labels, the interesting bit here is it says, set the position of the canvas to follow the mouse. Right? But what makes this interesting is that we've got this delay method. In fact, if I comment that out, let's just run this now. See as I'm moving the mouse around, I've got all of these letters now are under the mouse pointer. They're all overlaid on top of each other. And you could do this with events really easily. You don't need observable for this. But simply by uncommenting this delay, by delaying each one an incremental amount, what happens now is that they lag behind. And so you can do some really nice things with very little effort once you get over the weirdness to not be using events. We've got so used to events being the way to do it that we don't realize that there's another way that's much better than events. This is another example. Eric Meyer wrote both of these. Now this one here, this is a Windows Forms example. And what we're doing here, when we run this one, we've actually created a paint we can actually write on this. We can draw on it. And we're doing this entirely with RX. So that's the query we're doing there. We're doing a select and a switch. And I've handled the size change just to do to recreate the graphics object, and that's it. So it's pretty amazing what you can do with a few of these operators on that. And final thing, I think we've got some time. Yeah, final thing I'm going to do is we're going to show how you can use observables together with tasks. Because a lot of what people ask is when do I use tasks, when do I use observables? And there's some confusion created because reactive extensions actually came out in Framework 3.5 before tasks, and so they kind of allowed you to do some of the things that you would now do with tasks. And so some people say, well, I'm familiar with reactive extensions, tasks suck, we don't need them anyway, we can do everything with observables. And some people say, no, tasks are much easier. And the reality, it's like saying having a competition between values and arrays, or values and sequences. And the answer as to which you use, it depends. Well, there's two parts to it. Let's say you've got a method and it returns something. And if it returns a customer, you'd return a customer object. If it returns an array of customers, you'd return an array of customers. That makes sense. Now, if it's a time-based, let's say it returns a customer in the future, you would return a task of customer. If it returns a stream of customers in the future, you return an observable of customer. It's as simple as that. You use whatever type fits the scenario. Now, using an observable to return a single customer in the future is a bit weird. It's like using an array to return a single customer. If you've got a method called getCustomers, and it returns an IEnumerable of customer with one customer in it, you'd say, who wrote that API? And similarly with observables, if it returns just one item in the future, right, you return a task, not an observable. Observables are streaming for things. So that tells you in terms of whether you should use tasks or observables in your type system. There's a separate question, which is which API functions do you use? Do I await, or do I use the reactive extensions methods on it? And the answer is whichever solves the problem most easily. You can always convert a task into an observable. There's an extension method called toObservable, and often that actually works really well and it lets you solve problems. So there's nothing wrong with doing that. That's what you're supposed to do. So let's look at an example here, which is what I'm going to do is I'm going to write a mock method to download a web page. Right, this is going to make things simple. So it just does it jumps forward in time between 1 and 2 seconds, and then it returns you downloaded that URI. Simple enough, right? So let's run this with foo, and so it says you downloaded foo. Now, let's run this in parallel now. What I'm doing is I've got a link query which will take 5 web pages, foo1, foo2, foo3, foo4, 5, and by running this query, we're going to initiate 5 downloads in parallel. Now we want to jump forward in time to when all of them have downloaded. So this is what this does. This says jump forward in time to when they have all downloaded. Right, so let's run this, and we should get, when we run this, sometime later, we get 5 web pages. Now, there's something slightly suboptimal in here. Can anyone spot it? Yes, exactly. They're all arriving. In fact, some of them could arrive a bit sooner, right? If we could actually make use of those results as they arrived, right? Some of them may arrive at 1 second, some may arrive at 2 seconds. So if we can do that, wouldn't that be cool if we could just stream back these pages as they're arriving? So how do I do that? Exactly, convert the tasks to an observable. So what we're going to do, and that's what we've done in the next example. So we're now using, this is the extension method that converts a task to an observable. And now we're doing an RX query on this. So look what happens when we run this RX query. We can now see them coming down as they're arriving. So now we're mixing tasks and observables. Right? In fact, this is mainly an RX query. Now, we're going to get a bit more complicated in the last kind of 10 minutes, so this is going to get a whole lot more complex. We're going to now do something, we're going to change that to 50 from 5. That all works. Let's run that again. That all works, but imagine this was like a typical desktop internet connection. You wouldn't really want to initiate the parallel downloading of 50 web pages at once, would you? You'd just kind of throttle, you'll overwhelm the connection. It'd be better if we could throttle it to say no more than 5 at once. Now, how might we do that? How could we throttle that? Now, before you answer, there are ways that involve blocking. We're not allowed to block. We're obeying those 4 laws of time. So what are the solutions that we've got available? A queue. That's definitely one way to do it. That'll be my first thought, actually, would be a queue.
Change the range to observable?
Yes, change, but then how do we go from there? The problem is that we can't actually do it with observables. We can use a queue, but to me it's a bit suboptimal. There's no reason to have the queue if we can avoid pushing those elements in there to begin with. Why don't we just get those elements as we need them rather than queuing them up and pushing them and queuing them? If we're willing to queue, we could use observable, but in fact, the limitation of observables, that there is no way to exert asynchronous back pressure. So if you like, it's like an event. When something fires, it's got to be dealt with one way or another. You either have to deal with it, ignore it, or queue it up and create a queue structure. You can't sort of tell it, I'm not ready for you yet, come back to me when I'm ready. Right, so that's something interestingly you can do with Dataflow. There's an API called Dataflow, which is another NuGet package from Microsoft. It does allow you to do those queuing scenarios, and it allows back pressure. But anyway, there is a simpler way, a cool way we can deal with this, a simpler way, which is we can use a mixture of tasks and observables. So we can write a method which takes an IEnumerable of futures, an IEnumerable of task, and returns an observable. And it allows you to specify the maximum level of concurrency. Now, I've written that method. So what we're going to do is just look at how you call it first. before we look at the method itself. So here it is. I've created now, this exactly as we did before. I've created 50 tasks to download web pages. Now that highlighted blue code, does that start them all running? No, why not?
It hasn't been enumerated.
Exactly, it's not been enumerated. So it's got it all set up, but it's not actually running. So the trick is what this method does, this limited concurrency, it takes in the enumerable of task and it returns an observable. But because it's taking in a lazily evaluated sequence, it only pulls them at a rate it can handle. It doesn't bite off more than it can chew. So first it bites off 5 of them, if you've got 5, gets them all running. And as soon as one finishes, it bites off another one. It pulls another one from that input sequence. So we're combining pulling and pushing. Right? We're pulling from the input and we're pushing onto the output. And the output is an observable. That returns an observable of string. So we can run this now. And it's now going to maintain that perfect level of concurrency with not more than 5 running at once. And the other thing, so what we've effectively done with this is, this code is pretty complicated. This needed peer review. The first time I wrote it, I made a mistake. But it is something that you can write, and you only have to write it once, and then you can keep coming back to it. We're using locks here. This is hardcore concurrency stuff. So once you've written this, that's it. You can get it peer reviewed, and now, whenever you want to use that, this is all you have to do. And your business logic is completely clean of all this nasty concurrency stuff. You've simply got one nice declarative method with limited concurrency, and everything works sweetly. So, okay, before we go to questions, go back to the... Okay, we'll summarize. So to summarize what we've done, it's about isolation, simplifying concurrency by isolating concurrency from your business logic and isolating time from concurrency. And we looked first at latency, the idea of a value that comes in the future, and that we use a task to deal with latency. And for the streaming scenarios, for a latent sequence, we use observables. So they lessen the need for concurrency, they isolate it, and they shift concurrency problems into time problems. So, and then here are the 4 laws of time that were taken out. So that was a duplicate slide, which I deliberately put in there. So the 4 laws of time, we'll go back, find them. Here we are. No toxic long-running methods, separation, the TARDIS, and the composition. So we could summarize really by saying that it's all about giving time the same respect to space. The same abstraction patterns and attitude we have to work making life easy in space problems, we also should apply to time problems. Now, one of the issues that you will come up against when you start doing this is a learning curve, particularly with reactive extensions, with less so with tasks. But I want to tell you, though, that learning curve, if you take it on, you are voluntarily taking on a learning debt that at some stage you'll repay. If, on the other hand, you do not use these technologies and you allow concurrency concerns to seep into your application and business logic, you are taking on a technical debt that you will never repay. It will only accrue interest. Now, for related content, now firstly, all these examples that they're available on LinkPad. So what you do, if you want to download these, is go to LinkPad samples and click the download import more samples. And it will bring up a web page, and at the bottom, these are the samples of this presentation. You just click that download into LinkPad, overwrite, oh, sorry. Here we are. So this is a download import more samples. You click on that, and you click the download into LinkPad, this one. At the bottom is the samples for TechEd. And then that will give you this tree, this extra node in the tree, and you can run through all these samples. Now, I've also got, I've written another sample library, which is a tutorial on asynchronous functions, this one here. So it's definitely worth going through that one as well. And I've also written a book on which covers asynchrony in in some detail, which is C#5 in a nutshell. Reactive extensions, you can download that on Codeplex, and there's a NuGet package for it. It's definitely worth playing with reactive extensions. And Stack Overflow is a great place, as are the Microsoft forums. And I'm also going to be talking about LinkPad today at 1 p.m. at DevDen. So yeah, thanks everyone. We've got a few